Everyone, so today we're going to talk about waves. Now there's three types of waves. The first type is called a transverse wave, and they look something like this. I'm going to talk more about these two first types in a bit, so I'm not going to give you much background information about them yet. So we have transverse waves, and then we also have longitudinal waves, which look like this. The third type of wave I'm not really going to get into in this class too much, but it's called a surface wave, and surface waves are created by wind, basically, and we see them in the ocean a lot. And basically what they are, it's kind of a combination between a transverse wave and a longitudinal wave. And you can see that the surface waves kind of move in a circular pattern, as you can see in this little animation down here. So like I said, we're going to talk more about transverse and longitudinal waves, not so much about surface waves in this class. So here's another kind of animation of a transverse wave versus a longitudinal wave. So you can see in the transverse wave, the slinky is going up and down as it moves to the right. But in the longitudinal wave, the slinky is going back and forth as it moves to the right. And that's kind of like the definition and the difference between a transverse wave and a longitudinal wave. So a transverse wave, the medium moves perpendicular to the direction of the wave motion. I know my little camera's in front of motion, but it says motion. So what this means, perpendicular, remember that means a 90-degree angle, meaning like this. So that wave is moving up and down, but it is propagating to the right or the left. All right, propagating side to side or moving side to side. That's what propagation means. So we know the particles are going up and down, but the wave itself is going side to side. All right, so that direction, it's perpendicular to one another. So an example, a common example of a transverse wave is the wave. If you guys have ever been to like a baseball game or a football game or something like that, and they do the wave at, that game, in order to pump the crowd up, right? This is a transverse wave. So you can see in the wave, people move up and down out of their seats and they move their arms up and down, but the wave itself is going past them. So that's why it's called, that's a form of a transverse wave. All right, so let's talk about the anatomy of a transverse wave. So again, this is what a transverse wave looks like. First and foremost, we have the top of those wave peaks, and we call those the crests. And this kind of makes sense, right? You have heard that word before, the crest of a hill or something like that. So all of those peaks are called crests. Now the bottom here might be a word that you haven't heard of before. This is called a trough. That's how you pronounce it. It's kind of like an F sound at the end, trough. And if you have ever heard of a horse trough before, maybe if you've been horseback riding or something like that, it's what the horses drink and eat out of. And it's a bowl, basically, like a big, big bowl because they're big animals. But look at how that thing is shaped at the very bottom, right? It's kind of shaped like a bowl. So that's how I remember what it's called. It's called a trough, like a horse trough. Now this arrow that's already on here, right here, it's a measurement from the midpoint to the crest of the wave, or you can also take the measurement from the midpoint to the trough of the wave. It's going to be the same if we have a uniform wave like this, and that's called the amplitude. We denote amplitude by a capital A, and that's just the distance from the midpoint to the crest or from the midpoint to the trough, okay? The amplitude is not a measurement from all the way from a crest to the trough. That's 2 times the amplitude. If you want just one amplitude, from midpoint to crest or midpoint to trough. And now the last measurement on here, we call this the wavelength. Now wavelength is denoted by an upside down Y, which is called lambda, all right? We're running out of letters in physics here. So we're now going to be digging into those Greek letters. So this is a Greek letter called lambda. Now the wavelength here is measured from crest to crest, and it's just the length of one wave, right? Wavelength, length of one wave, easy to remember. You can measure it from crest to crest like this. You can also measure it from like trough to trough, or you can take a measurement from one of the midpoints, like where a wave starts. So for example, it could start at the beginning right here, and then you have a crest and you have a trough, and then it would end after that. So it's just the length of like one complete wave. That's what a wavelength is. Now, a longitudinal wave, on the other hand, the medium moves, and let me move this so you can actually see the writing. The medium moves in the same direction as the wave movement, meaning you saw that on the slinky before, right? That slinky moved side to side as the wave went by. So the particles in a longitudinal wave are going to move side to side as the wave goes through them. So they're moving in the same direction or parallel to the wave movement, or the wave propagation is what we call it. Now, a example of this could be a wave on a slinky. This is a very common example because it is kind of hard to actually visualize a longitudinal wave. A real life example of a longitudinal wave are sound waves, because we have particles in the air, and as sound moves through them, it's really just those particles moving back and forth like this, creating pressure differentials. But the easy way to see it is a slinky wave. So I'll show you this video. So you can see he's moving his hand back and forth, and we're getting those kind of pulses, right, as that wave moves. So that's our longitudinal wave. The direction of vibration is back and forth. The direction of the wave is to the left in this case. Now, just like we had the parts of the transverse wave, we also have parts of the longitudinal wave. So the first part is called a compression, all right? And that makes sense, right? Those particles are compressed together. That makes total sense. Now we can see one other compression on here. So if you already pointed it out with your eyes, good job. That's our other compression. Now, the areas where the particles are spread apart, this is probably a word you've never heard before. This is called a rarefaction. All right, rarefaction, where the particles are spread apart. And so again, we have another rarefaction over here, and I'm sorry, my picture's covering it. We can also find a wavelength on the longitudinal wave as well. We can measure from compression to compression. Notice how that measurement is from the middle of one compression to the middle of the next compression. You can also measure from the middle of one rarefaction to the middle of the next rarefaction, or another way is you can find like a complete cycle of the wave, meaning you can go here, it's from like the beginning of one rarefaction to the beginning of the next rarefaction. So one complete cycle. Again, all of these lengths will be the same if it's a uniform wave. So we've talked about the different types of waves, and we've talked about, the different parts of those types of waves. And now we're going to kind of get into other, things that waves do, and other just things that they display. So we're first going to talk about what the speed of a wave depends upon. And there's only actually one thing that the speed of the wave depends upon. And you'll see this when you're doing your activities and things like that this week. So the speed of the wave, the only thing it depends on is the medium that the wave is traveling. Meaning like the material. So either the air that we're breathing, the ocean, you can see that there's a whale right here and it's making those whale sounds. If you've ever heard them, they're very calming. But that whale is able to make those sounds, and other whales are able to hear it under the ocean because sound can still travel through water and through the ocean and things like that. Sound can even travel through solid materials like steel and things like that. So the question here is, do you think that sound waves travel faster through air, water, or a solid like steel? Think about it for a second. Now, the answer here is that sound waves and waves in general actually travel faster through more solid material. So sound waves really, because if we're talking about like ocean waves, obviously those are in the ocean. But if we're talking about a wave that can travel through all three of those states of matter, they're always going to travel the fastest through the most solid material. So the reason for this is because the particles are closer together. So if I show you this video here, here you can see that we have a solid, and in a solid, those particles are really, really close together. So because they're really, really close together, when one particle hits the next particle, that space between those two particles is super, super close. So it immediately hits the next particle, which then hits the next particle and propagates that sound wave super, super fast. Now in a liquid, you can see that these particles are a little bit farther apart. So it takes a little bit longer for that particle to hit the next particle and then go on and propagate that wave. And then in a gas, the particles are even farther apart. So it's going to take a lot longer for that particle to come hit the next particle and propagate the wave. So that's why things like sound waves are going to travel faster in solid material. You can actually try this and kind of experiment with it at home if you want to. If you have like a brick wall or maybe a chain link fence with one of those steel tops or something like that, if you put your ear up to it and then have your brother or sister or family member knock on it with like a spoon or just their fist or whatever, kind of far away from you, you'll actually hear it in your ear that's pressed against the solid material before you hear it in your other ear. So it's a very interesting little science experiment to do at home. All right, so let's talk about some other properties of waves. So we have frequency. Now, frequency, you've probably heard this word before, like the higher the frequency means it's more frequent, right? And that word just makes sense. Now I have a little clip from the Bill Nye video about waves on frequency because I think it is it's very helpful because he gives you kind of a visual and he explains frequency very well. So I'm going to show it to you and then we're going to talk about the definition of frequency afterward.
If waves all look alike, how can we tell them apart? Well, please consider the following. If waves are nice and even like these, we can't really tell them apart unless we stand in one place. This is our observer kid on a stick. And where she is, she can see the top of one wave. Then as the waves go by, she can see the top of the next wave. Now the distance from here to here, the length, is called the wavelength. That's what we call it, the wavelength. Now, there's another thing about waves that you can observe, and it's called the frequency. If you go to the library often, we say you frequent the library. That's how often you go there. So waves like this are coming by often, and we say they have a high frequency. If I slow it down, the waves coming by have a low frequency.
Okay, so that word frequency makes sense, right? And I'm going to move my little picture over here. Okay, so the definition of frequency is the number of waves per second, right? Now, the way that we find this, if we're given information, is the number of cycles or the number of waves over the number of seconds, really. But if we're given the number of cycles in 1 second, that will give us the frequency. So the unit for frequency is called a hertz, and it's just denoted Hz. And 1 hertz is equal to 1 cycle or 1 wave in 1 second. So if I say that this wave has a frequency of 1 hertz, it just means that there's 1 wave happening in 1 second. So an example of this would be if Billy observes 5 ocean waves in a period of 2 minutes, what is the frequency? So we need cycles or waves divided by the number of seconds. So here we have 5 on the numerator divided by 2 minutes, but we need seconds in order for it to be hertz. And so if we convert 2 minutes to seconds, it's 120 seconds. So we end up getting 5 waves divided by 120 seconds equals 0.05 hertz. So if he's observing 5 waves in 2 minutes, it's not a very high frequency, right? Which is why this number is super, super low. It's 0.04, right? That's a very low frequency. Now, sound waves are measured in the frequency. It's measured in hertz. And if you're a musician, you probably know that the middle C is 256 hertz. So that's a much higher frequency, right? And it's because those sound waves are oscillating back and forth at a much, much higher rate, a higher frequency, all right? If you know more about music, and we're actually going to talk more about music next week, but higher pitch sounds are higher frequency sounds because those oscillations are much, much more frequent, much, much higher than lower pitch and lower frequency sounds. All right, so let's talk about period now. It's very similar to well, it's related to frequency. It's not, I shouldn't say similar, it's related to frequency. So period is the amount of time for one complete cycle of a wave in this case. And period is the inverse of frequency, which means that higher frequency waves have lower periods. Okay, that's what inverse means. Lower frequency have higher periods. And what this means that if we have a higher frequency wave, it takes less time for one wave to happen. So let's say the frequency is 2 hertz. The period is the inverse. So it's just 1 over the frequency. So 1 over 2 or 0.5 seconds. And this makes sense, right? Because if the frequency is 2 hertz, that means 2 waves are happening in 1 second. All right, 2 waves in 1 second, which means that if we want the time for one wave, that would just be half a second. Okay, so that's the relationship between period and frequency. If you want equations for this, this is what it looks like. So period, capital T, is 1 over frequency. Frequency is 1 over period. All right, so that's the relationship between period and frequency. All right, so we're now going to talk about some wave behavior, okay? So constructive and destructive interference. Now, all I'm going to do is show you pictures of these, and I'm kind of going to walk you through them a little bit. So make sure you listen carefully. If you don't understand these things still, you can look them up online also, okay? Because I didn't actually write a definition on these slides. So here's a picture of constructive interference. Now, constructive interference occurs when 2 waves are what we call in phase with each other, which means that they're pretty much the same wave, right? You can see the blue wave on the top and the red wave on the bottom. Those crests line up and then the troughs line up. So what happens when these 2 waves are in phase with one another and the crests are lining up with the crests, the troughs are lining up with the troughs, when they add together, we actually get a resultant wave, which is the green wave right here, that has an amplitude that's just equal to the sum of the other amplitudes, all right? So we get a resultant amplitude that is larger than before because those 2 crests are being added together, the 2 troughs are being added together. I like thinking of constructive interference like construction, right? When you have construction, you have buildings being built up. Okay, so what's happening when we have constructive interference is that those amplitudes are being built up. Now, destructive interference, on the other hand, you probably can tell from the actual name, destructive, like destruction, right? This happens when 2 waves are out of phase with one another. So we can see that the crest of the blue wave is lining up with the trough of the red wave, and then the trough of the blue wave is lining up with the crest of the red wave. So what's happening is a lot of students like to say these things cancel out. And yeah, they're adding together, but one's positive, one's negative, and vice versa. And so when that happens, they add together, but then they basically cancel out if they're perfect, you know. I like to call up positive and down negative and say like a +2 and a -2, and they add to 0, right? So what happens, they add together, you get destructive interference and no amplitude at all. Of course, if these waves aren't like perfect mirror images of one another, you could just get a smaller amplitude. But in this case, we'll say that this is like a +2, this is like a -2, and so that's why you get 0 amplitude over here. Okay, so that's constructive and destructive interference. Now, when waves are reflected off of a barrier, we get an interesting thing that happens because it actually depends on the type of barrier where the wave is reflected. So we can see on the top here, we have that string right there, that red and white string is actually tied to that pole at the top. And we can see that when this, we call it an incident wave that's coming in to the right toward that barrier right there. When the incident wave comes toward the barrier, it actually hits that barrier, and that's called a fixed barrier because it doesn't move, and it's reflected underneath, right? So it's actually opposite the incident wave. Now on the bottom here, when we have our reflected wave and it hits the barrier, that's a loose barrier, or a free end is what we like to call it as well. And because it has like a hook or like just a circular ring that's around that thing and it's able to move up and down, right? So when that incident wave hits the free end, then it's actually reflected back on the same side as the incident wave, okay? So when we have a fixed barrier, sorry, I'll move myself again. When we have a fixed barrier, the wave reflects on the opposite side of the incident wave. So this is the reflected wave reflects on the opposite side. And when we have a free end, the wave reflects on the same side as the incident wave. And so you can see that from this animation at the top here. Now, the whole reason that I give you all of this information about constructive and destructive interference and reflection of waves on a fixed barrier and a free end are because this interference and reflection are two properties that influence what we call standing waves. Okay, so standing waves are created when an incident wave and a reflected wave interact with one another. The interaction causes a resultant wave that looks like it's standing still. And I'm going to show you an actual animation of this, not just this one that I have here, but a simulation type thing. But we can see if we call this end right here on the right that fixed barrier, we have an incident wave that is yellow in this case, and then the reflected wave would be the other one. When they add up together, so the crests add up or the troughs line up here, we get the highest amplitude, okay? And then this resultant wave, which is a combination of both of them, the pink one, is what we call a standing wave because it kind of looks like it's standing still. Okay, so let me show you that simulation because it's a little bit easier to see. So I'm going to start it because it goes kind of slow also. So this red wave that's coming in right here is what we call our incident wave, meaning someone's at the end making this wave. All right. Now, of course, this is a transverse wave because we can see that the particles are going up and down, but the wave is actually moving to the right. Okay. But these standing waves can actually occur with longitudinal waves as well. Okay. So the red wave is hitting this barrier. It's a fixed barrier. So the reflected wave is the blue wave. Okay. So now you can see that when the reflected wave, which is the blue wave, and the red wave, which is the incident wave, when they line up together like that, you get what we call an antinode. And I'll get to that also in a second. Okay, you get constructive interference, which makes that really big amplitude. And then when they are out of phase, right, this is in phase right here, and then out of phase there, we get destructive interference, right? Okay, so you kind of see this is how a standing wave is made. Now, antinodes here are the areas where they have the most movement back and forth. Nodes with the little n right here are the areas that look like they're actually standing still. I like to remember it as nodes, no movement with nodes. Get it? Kind of. So these are standing waves. Now, the reason that I wanted to talk about standing waves and I actually wanted to end with standing waves is because standing waves are very important in music. Next week, we're going to talk about music a little bit more. So I just wanted to kind of introduce this concept of standing waves and how they're made so that we can have kind of an introduction into that, and then we can segue into our stuff next week a little bit easier. Okay, so that was just a little bit of information about waves. I hope you guys found it interesting. Let me know if you have any questions. All right, feel free to email me at any time, and I will see you next time. Bye, guys.